All right, section P3. Okay, this is all about square roots. We're going to take lots of roots in this section. We're going to work with radical expressions as well, okay? So the principal square root of A is denoted by B equals the square root of A, okay? And that square root is always going to be positive or 0. So for example, the square root of 25 equals 5 because 5 squared equals 25. All right, and the only way that you're going to get a negative answer, specifically for a square root, okay, that's important, is if the negative sign is out front. Okay, so what do I mean by out front? So look at this example here. We have the negative square root of 64, okay? So some students like to say that this that I'm highlighting here is like a house. So 64 is under the house. So the only way that you're going to get a negative answer for a square root is if the negative sign is outside the house, okay? Not inside the house, okay? So then we get -8 in that case. So that's the only way that we're going to have negatives running around, okay? With square roots. All right, here's a list of squares, okay? Just from 1 to 10, I squared each value. We're going to use this list. It's going to be on the next page as well for you to look at. But this is just a list of squares that we're going to use a lot. And you're probably familiar with at least some of them, okay? So there it is at the top right. So if we had examples and we needed to simplify the radical expression, okay? And we had something like the square root of 49. All right, well, we can go over to our list of squares and we have 7 squared equals 49. So that means that the square root of 49 equals 7 because 7 squared equals 49. Okay. Now, let's do another example. What if we put a fraction under our radical? Okay, so we can say, okay, this is the square root of 1/9. So we can take our radical to the numerator and to the denominator. So we have the square root of 1 over the square root of 9. Okay, so we just took the square root to the top and to the bottom. And we know that the square root of 1 is 1 because 1 squared is 1. And we know that the square root of 9 is 3 because 3 squared equals 9. So our answer is 1/3. What about the negative square root of 81? Okay, and if you remember what I said just a second ago about negatives, we are okay here because our negative is outside the house. Okay, it's not inside, it's outside. So that we know we're going to end with a negative number. And the square root of 81 is 9 because, let's go up to our squares. Where is it? There it is. Because 9 squared equals 81. So the square root of 81 is 9, and we're going to leave our negative sign there because it's outside the house. All right. Well, look at this one. The square root of -36. Notice the way that I said these two different examples. Up here, I said the negative square root of 81. And on this one, I said the square root of -36, okay? The problem with this guy is that the negative is inside the house. And that is illegal. We don't like that. That is a no-no, okay? So this gives us an error. If you typed that into your calculator, you would get an error, okay? Actually, it's just technically not real. It's not a real number. It is a complex number, and we will get to all of that soon, okay? But for now, all you need to know is that if you are taking the square root of a negative number and your negative is inside the house, that gives you an error. That gives you something that is not real, okay? So, couple of rules. Here's the first one, and we've been doing this one, right? The square root of a squared equals a. So this means that if we had the square root of 3 squared, so your 3 is acting like your a in our generalized rule here. So we just get 3. Okay, so what that radical sign is doing here is undoing your squared term, okay? If I'm squaring something and then I take I square root it, I'm undoing the fact that I squared it, okay? Kind of like how we talk about division undoes multiplication, or multiplication undoes division, okay? So here's a rule that we're going to use. Let's see, next page. Here's another rule, okay? If A and B represent non-negative real numbers, okay, so that just means that they're positive numbers, then the square root of A times B equals the square root of A times the square root of B. So all this is saying is, hey, if you give me a radical, if you give me a square root or any kind of root, and I'm multiplying two numbers under that square root, then I can break it up into one thing multiplied by the other thing. Okay, that's all. So this rule comes in handy when I give you something like the square root of 12, okay? The square root of 12, there's nothing in our list of squares that helps us out, okay? We don't have anything that is a perfect square, okay? Nothing that when we take the square root of it, it's going to give us a whole number, all right? But we do have factors of 12, right? So we think, okay, what are the factors of 12 that are going to help us out? Okay, so we have 4 and 3. Okay, another two factors of 12 are 6 and 2. But also 6 and 2 are not perfect squares. Okay, there's nothing that we can't take the square root of 6 either to get a whole number. It doesn't work. So we're still kind of left in the dark there. But we can take the square root of 4 and get a whole number, okay? So because of our rule up here, we have two things multiplied together under our radical. So that means that we can split it up. And we can say that we have the square root of 4 times the square root of 3, okay? What is the square root of 4? Go back, look at your square, your list of squares that we had. It's 2, right? So this is no longer the square root of 4 because we can simplify the square root of 4 as 2 on the square root of 3. Okay, that's how we say that, 2 on the square root of 3. You can also say 2 times the square root of 3. So if I say either one, I am referring to the same thing. Okay, so we said, nope, we know what this is. That is 2. Okay. square root of 45. Again, it's not going to take you very long to realize that we don't have any perfect squares going on here. We can't just take the square root of this and it be a whole number. So we need to think of the factors of 45 that are going to help us out, okay? Well, 9 and 5. 9 times 5. We're going to apply our rule once again. Whoops. Apply our rule. We're just going to break it up. And we know that the square root of 9 is 3, because 3 squared equals 9. So we have 3 on the square root of 9, because we said, hey, we know what this is. And we get 3. $75, the square root of 75. Once again, not going to take you very long at all to say, hey, this is not going to give me a whole number. I can't take the square root of this and get something that helps me out. So I need to think of the factors of 75 that are going to be helpful to me. Okay, so you're looking for numbers like 4, 9, 16, 25, 36. All of those are going to help you out. All right, so you have 75. Okay, well, that's 25 times 3. And you said, okay, Ms. Kelly, that's great that you figured that out, but how am I supposed to figure that out? Well, just go down your list of squares and say, well, 4 can't go into 25, and 9 can't, and 16 can't. And then you get to 25 and you say, oh, 25 times 3 is 75. So that's what I need to split my radical, my number into, okay? So just go down that list, all right? So now you say, all right, apply your rule. So you get the square root of 25 times the square root of 3, and that gives you 5 on the square root of 3. Okay, and you said, hey, I know what this is, that's 5. Okay. So these 3 examples, I ran into an issue and said, okay, these are not anything that's going to be helpful. Like, I can't just do this in one step. I have to break these up. I have to use my rule that says if I'm multiplying 2 numbers together under a radical, I can split them up and take the square root that way, okay? Here's another rule. And we have already used this rule actually in a previous example. Here's a rule. It says if A and B are represent positive real numbers, then the square root of A over B equals the square root of A divided by the square root of B. Okay, so all that's saying again is that I can split it up. I can do it by pieces if you want to think of it like that, okay? So earlier we had the square root of 1/9, and we got the square root of 1 over the square root of 9. Okay, and that simplified to 1/3. Now, let's look at some maybe more complicated examples, all right? So we have the square root of 98x to the 11th all over 2x cubed. And all of that is under a radical. Okay, so your first step, let's deal with your fraction, okay? So we have 98 divided by 2. Well, you have a calculator, and you're just going to divide like you normally do. Nothing changes there. So you get 49. 98 divided by 2 is 49. Now you need to deal with your x's. And if you recall, if you are dividing like exponents, meaning you have an x and you have an x, so I have an x here and an x here, I'm dividing these two exponents. So I subtract my exponents, okay? So I'm saying x to the 11th over x to the 3rd. So I'm saying 11 minus 3. So I get x to the 8th. All right, do you guys see that I just dealt solely with my fraction? I didn't deal with my square root at all. At all. And we can make a note what we did with our exponents. We were dividing our exponents. So we subtract. Okay, so we said 11 minus 3, and we got 8 right there. All right, but we didn't touch our square root, okay? Now let's deal with it. Let me zoom out a little bit. So from here to here is where we will deal with our radical. All right, so we are taking the square root, right? And we normally don't write a 2 right here, but it's going to help us keep us straight, all right? Because there's an understood 2 right there. We're taking the square root. That is the principal square root, okay? So let's write a 2 right there. So we are going to take the square root of 49. All right, well, that's just like the very first example that we worked. That's just a normal square root of a number. So we get 7 because 7 squared is 49. Now we have this exponent, this variable raised to this exponent, and we need to get that out from under the house, okay? Here it is under your radical, and we need to get it out of the house. So what you're going to do when your exponents are under the house and you need to get them out of the house, you are going to divide your exponent by whatever root you are taking. Okay, so I'm taking the square root here. So I'm going to say 8 divided by 2. Well, that's 4, right? So x to the 4th is what I would get. All right, so this is actually your answer right here. 7x to the 4th. And we can make a little note about what we did with our exponents here. So I'll circle them in the color and then write them in the color. Let's see. I can write right here. Okay. So we said 8 divided 2. We said, I'll just write it in words, that we divide exponent by the root. Okay, so we say, all right, so we have 8 divided by 2 gives us 4. Okay. Let's do another one. The square root of 75 x to the 10th over 3x to the 4th. Okay. Once again, we are going to start with our fraction from here to here. Don't even worry about the fact that you are taking a square root. Not yet. We're not worried about that. So now we're going to put back our square root because we're not dealing with it yet. Deal with your whole numbers first, your coefficients. Okay, those are these guys, your coefficients. And you have 75 divided by 3. That gives you 25. And then remember what we do to exponents whenever we divide, we subtract our exponents. So we are saying x to the 10th, x to the 4th. So we say 10 minus 4, that gives us 6, okay? So we dealt with our fraction, we didn't touch our root. Now let's deal with our radical. All right. So once again, we're taking the square root. So deal with your whole number first. You have the square root of 25. Well, that's going to give you 5 because 5 squared equals 25. All right. Then you have to deal with your variable raised to an exponent. Okay. And remember what we did last time. You divide. So you say, okay, here's my exponent. Here's what my root is. I'm going to say 6 divided by 2. That gives me 3. All right, and I'll write, oops. 6 divided by 3 gave me 2. And I'll draw lines. And I'm sorry, I wrote that wrong. 6 divided by 2 gave me 3, my bad. There we go. And so your answer is 5x cubed, okay? So all I did was I gave you 2 rules. I gave you one for multiplication, one for division, all right? So we can also add radicals, but we can only add radicals if they are alike. Very important. Add radical if they are alike. Okay, so the square root of 5 and the square root of 7, obviously those are not the same. We cannot add those together. The square root of 5 is different from the square root of 7. Also, 5 and 7 are prime numbers, meaning the only factors of 5 and 7 are 1 in itself. So 1 and 5 and 1 and 7. So we can't even break it down and use one of our rules that we have. We can't even use one of the tools that we have in our toolbox to simplify this down to something that could possibly give us something that is alike. So this one, not alike. And we cannot simplify this any more than it's already simplified. So this right here is this expression in simplest terms, okay? What about this one? 5 on the square root of 3 plus 9 on the square root of 3, okay? Remember, we can only add radicals if they are alike. Well, the square root of 3 is the same as the square root of 3. So what we do, because we have this and this, we get 14 on the square root of 3. Okay, so we added, once again, we added our numbers. Okay, we did not add 3 and 3 and get 6 because the fact that we had square root of 3's didn't change. We just have more. So I had 5 square roots of 3, right, in my possession. And you gave me 9 more of them. Well, that just changed the fact that I now have 14. It didn't change the fact that I still have square roots of 3's, right? It only changed how many of them I have. So your square root of 3 does not change. Only the amount of them that you have changed, okay? Well, same thing here, right? The square root of 2 and the square root of 2. So I'm good when in regards to the fact that I can add and subtract them. They are alike. Okay, so I have 11 on the square root of 3, 11 on the square root of 2 minus 4 on the square root of 2. And now I need to subtract my numbers. So I have 11 on the square root of 2 minus 4 on the square root of 2. So I'm saying, this is like saying, all right, I have 11 square roots of 2, and you come to me and you take away 4 of them. So I'm left with 7 on the square root of 2, because it didn't change the fact that I still have square roots of 2. It just changed again how many I had. So you're not doing 2 minus 2 and getting the square root of 0. Those are all staying the same because it's not changing how many of them, or the fact that I have square roots of 2. It's just changing how many of them that I actually have. Okay. So you get 7 on the square root of 2 as your answer. All right, let's look at this one. 5 on the square root of 27 plus the square root of 12. Well, you say, nope, we can't do it. We can't do that. They aren't the same. The square root of 27 and the square root of 12 are not the same. And if you told me that, I would say that you're right. But there's something that we can do. There's a rule that we have. There's a tool in our toolbox that we have that says, hey, I have some factors of 12 that can simplify this guy. And I have the factors of 27 that can also simplify this guy. So let's do that. I have 5 on the square root of 7. So I'm going to keep my 5, draw my square root sign, and say, okay. All right, 27. What are the factors of 27 that could help me out in simplifying this? All right. Well, you could go down your list. You need to start thinking, okay, well, 1, of course, 1 and 27, but you'd still be left with 27. 4, that doesn't help. 9 times 3 is 27. All right, so let's stick with this guy first and finish him before we go to square root of 12. So we have the square root of 9. Well, the square root of 9 is 3, right? So we're going to bring our 3 out in front. And this is no longer there. Okay, so we did not bring out a 9. That's something that students do a lot, is they bring out a 9. But you are taking the square root of 9. Okay, you have to take the square root of this in order for you to get it out from under the house. You can't just bring it out here, because if you brought it out, it would still be the square root of 9. Okay, you took the square root of 9 and you got 3. So that's what you brought out. And so you have 3 times 5, that gave you 15 on the square root of 3. Okay, you still have a 3 left under your radical. Okay, so that's what we get for 5 on the square root of 27. Now you need to deal with the square root of 12. So change colors. What are the factors of 12 that will help me out? We already worked one with the square root of 12, and we said, okay, 6 and 2 don't help us. All right, that's not, you have 1, 4, 9, 16, 25. 6 is not in there. 6 is not going to give you anything you want, but 4 will. 4 times 3. And you say, okay, what is the square root of 4? And it is 2. So you bring a 2 out. So you get 2 on the square root of 3. Notice again, we did not take a 4 out because we had to take the square root of 4 in order to get it out of the house. So we get 2. Okay, well now look what happened. Now we're left with 15 on the square root of 3 plus 2 on the square root of 3. Well, now we have like terms. Now we have radicals that are the same. Because they're the same, we can add them together. So we have 15 on the square root of 3 plus 2 on the square root of 3. That gives us 17 on the square root of 3. Okay. Now let's do this one. I want you to maybe pause the video for a second. Try to do this one by yourself, okay? Same process that we just did before, but this time we're subtracting. So pause the video right here, try to do it by yourself, and then I will explain it. Okay, so 7 on the square root of 18. 18, nothing about 18 helps us out. Let's think of the factors of 18 that would do us some favors, okay? So you're thinking 1, 4, 9, 16. 1, 4, 9, 16, 25, 36, 49. Okay, those are numbers that you need to be thinking of. You get to 9 and you remember, okay, 9 times 2 is 18. And the square root of 9 is 3. So you're bringing out a 3, not a 9. You're bringing out 3. And so you get 21 on the square root of 2. All right, let's work with 5 on the square root of 8. You have your 5 stays and you have the square root. And I need to multiply the factors of 8. So I have 4 and 2. 1 and 8 and 4 and 2. Well, 4 and 2 help you out because of 4. So you have 4 here. That gives you 2. Right? I didn't take 4 out. I took 2 out because the square root of 4 is 2. So I have 2 times 5 is 10 on the square root of 2. Okay. Well, now I have something that I can subtract because these are alike. So 21 minus 10 gives you 11 on the square root of 2. Okay. So that had to deal with adding and subtracting radicals. All right. So we just added another layer to what we had just done, right? We had just gotten through with our 2 new rules that said, hey, I can multiply these. I have a rule that says I can break these down with multiplication and a rule that says I can break them down with division. So we took those 2 rules and said, well, what if we were adding things together? Okay, if they're not alike and they can't simplify, then they are just as simple as they can be. If they are alike, you're going to not change your radical, only change your numbers outside the house, okay? And then maybe sometimes I'll have somewhere I can manipulate my radicals into something that gives me the same root to where I can add or subtract, okay? All right, let's talk about now what rationalizing the denominator looks like, okay? Some big words there, but we're going to break it down. Okay, there's 2 types of problems in this objective. There's one type where there is a single term in the bottom. So 5 on the square root of 3, there's just one thing going on in the bottom. And then there's another type where there's 2 things going on in the bottom. All right, of course, you could probably guess that the one term is easier to deal with than the 2 terms, but we're going to go over both of them, okay? So I give you directions and I say, okay, I want you to rationalize the denominator. That means that I want an answer to this. I want you to simplify this to where there is no longer a radical in my denominator. Okay, that's what rationalizing the denominator looks like. So what I'm going to do, if I want to rationalize my denominator, is I'm going to multiply the bottom and the top. Whoops. The bottom and the top by whatever radical I'm given on the bottom. Okay, so I'm multiplying these 2 things together. So I have 5 on the square root of 3. And now I'm multiplying. I'm not adding these together. Okay, when I said that we don't mess with the number under the radical sign, that was when we were adding and subtracting. But here we're multiplying. So we're saying the square root of 3 times the square root of 3, that gives you, whoops, the square root of 9. Okay, not much you can do, not much of anything really that you can do to the top. You just have 5 on the square root of 3, okay? There's no, you can't simplify that down any, that is in the simplest form that it can possibly be. But your denominator, okay, you have the square root of 9. Well, that is 3, right? So we end up with 5 on the square root of 3 over 3, and that is your answer. Notice that I no longer have a radical sign in my denominator, do I? I just have a 3. So all I did was multiply both the top and the bottom by the bottom in a single term. Okay. Well, what about if I had 2 terms? We are going to multiply the top and bottom by something. All right, and that something is actually a fancy word. It's called the conjugate. We're going to multiply by the conjugate of my denominator. All that means is I'm going to multiply by 4 minus the square root of 5. So I'm multiplied both the top and the bottom by this expression. The only thing that changed was my sign. Okay, and that will happen every single time. Okay, these 2 numbers that you have will stay the same. If you're given a plus, you'll do a minus. If you're given a minus, you'll do a plus. Okay, you're just going to do the opposite of whatever you're given, and you're going to multiply both the top and the bottom by those 2 numbers. Okay, so we have 8 times 4 minus the square root of 5. Okay, so we are going to distribute the 8, right? We're going to say 8 times 4, and that gives us 32. And then 8 times negative square root 5, that gives us minus 8 on the square root. Keeps doing that. Square root of 5. Okay. Well, here we have on the bottom 4 plus the square root of 5 times 4 minus the square root of 5. All right, so we are going to, as we like to say, FOIL this because we have a binomial, 2 terms, times a binomial, 2 terms. So we say first, outer. I'll use a different color. Let me look. Inner, last. Okay. So first we had 4 times 4, that gave us 16. And then we had 4 times negative square root 5, that gave us 4 on the square root of 5 minus 4 on the square root of 5. So we went here first. We said 4 times 4, that gave us 16. Then we went outside and that said 4 times negative 5 square root of 5. That gave us negative 4 on the square root of 5. Then we have inner. So we have the square root of 5 times 4. Okay, that's plus 4 on the square root of 5. And then we had square root 5 times negative square root 5. Well, that just gives us, we're multiplying, so we have negative square root 25. Okay, well, look what happens to your middle terms. Okay, what's happening here? Negative 4 on the square root of 5 plus 4 on the square root of 5. Well, that gives you 0. So those are gone. And then what is the square root of 25? I'm trying to change my colors. There we go. The square root of 25 is 5. So 16 minus 5 is 11. So our answer here is 32 minus 8 on the square root of 5 over 11. Okay, we messed with that. Notice how my directions are rationalized in the denominator, and that means that I need to have my denominator with no radicals in it. Okay, notice how I accomplished that with multiplying by the conjugate. Okay, so as you can see, just a little bit more difficult than when we have just one term floating around instead of two terms floating around. All right. So far the rules that we've covered only involve square roots. We've only been taking the square root of all of these problems. But all of these rules hold true for higher powers too. Okay, so we can generalize what we've already said, and we can say, okay, if you're taking the nth root of a equals b, that means that b to the n equals a. Okay, we have had squares on all of ours so far. Okay, but we can generalize it into any root. Okay, and that n value right here is called the index. Okay, so here's some examples. So the fourth root of 16. The fourth root of 16 is 2 because 2 to the fourth gives us 16. Okay, so instead of squares, we're using 4s there. And then we have the fifth root of negative 32. Gives us negative 2 because negative 2 to the fifth is negative 32. Well, that should bring up some question marks for you guys in your head because we just made a whole point that you can't take the square root of a negative number. Okay, remember when I underlined square root and said this is important? That's because we're no longer taking the square root, we're taking the fifth root. Okay, so here's how we can generalize this part. If n is even, remember n is this number. Okay, if n is even, so 2, 4, 6, 8, 10, anything like that, we cannot simplify the radical of a negative number and get a real number. Okay, so anytime that we take an even root, that means if we have, let me get to here, if we have 2, if we have 4, if we have 102, okay, if this number is even, we get an error. Okay, in particular, on this problem, the square root of negative 49 is going to give an error. Okay, so this also equals 7i, okay, which is not a real number. It's a complex number, like I said, and we are going to cover that later on in chapter 1, okay? So for now, you saying, hey, you're taking the even root of a number, so that is an error. That is completely valid. I agree with you on that because you do not know any better yet. But if n is odd, okay, we had even here. If n is odd, you can simplify. the radical of a negative number and get a real answer. Okay, so we have the cubed root of -8. Well, that gives us -2 because -2 cubed is -8. Okay, and if you typed this into your calculator, you would get -8. Okay, so if you have an odd root, you're okay. If you have an even root, you're not. That's an error. All right. So here is a cubes list. We're going to work some examples. Here's a cubes list. All right, I didn't go very high because these get, of course, we're cubing it, not squaring it now. So these numbers get bigger very quickly. But we have 1, 8, 27, 64, 125. Those are the normal ones that you're going to see most of the time, okay? So let's do some examples. We have the cubed root of 125. Okay, if you go back to your other page there, you have your cubes list. 5 cubed is 125, so we get 5. The fourth root, we can write out some fourth roots. Hold on. 1 to the fourth, 2 to the fourth, 3 to the fourth. 1, 2 to the fourth is 16, 3 to the fourth is 81, okay? So on the fourth root of 81, 3 to the fourth is 81, so we get 3. The cubed root of 125 over 27. Well, our rules that we learned a couple of pages ago still all apply to greater roots than square roots. So we have, it keeps doing that. The cubed root of 125 over the cubed root of 27. Okay, so this was our division rule that we had a couple of pages ago. So we have the cubed root of 125. Well, 5 cubed is 125. So we have 5 over, and the cubed root of 27, 3 cubed is 27, so 3. The cubed root of 40. If you go to your cubes list, you'll notice very quickly that 40 is not on there. So we don't have anything that's just going to give us a whole number right away. But our rules still apply, right? So we have the cubed root here. And we're looking for the factors of 40 that help us out. Okay, in our cubes list, we do have 1, and then we have 8. And 8 times 5 is 40, right? So 8 is here. The cubed root of 8, I'm not doing the square root of 8, I'm doing the cubed root. So the cubed root of 8 is 2. So I'm going to multiply this by 2. So I'm going to get 2 on the cubed root of 5. Okay, don't forget to write your cubes there. Okay, it's a habit of you to not have to do that because of the fact that you're used to doing square roots, but we need to remember to write our cubes, okay? The cubed root of -27, okay, look right here. This is odd, so we're okay. The cubed root of -27 gives us -3. The square root of -25, this guy is even. So we get error. Okay. This is even. 12 is even. So we get error. negatives under the house, but this is odd, so we're okay. And the cubed root is -2. This one is even, so we get an error. This is just square root of 9. Okay, back to the basics here. This is even. So we get 3. Okay. So I went pretty quickly on those because I needed to look at whether or not I could even work them. Okay, if it had an even root and it had a negative under the house, I wasn't even allowed to work it. I just write error. Okay. So there's putting a lot of what we've done together. And now I'm saying, well, now I can apply all of these rules to different roots. Okay. I can have any root I want and I can still apply those rules. Okay. Well, rational exponents have something to do with square roots and roots of that sort. Okay, a fractional exponent means to change to a radical. So here's a rule basically. A to the 1 over n equals the nth root of a. Okay, so I took my denominator of my exponent and moved it to the index spot. Okay, so instead of writing 16 to the 1/2, I would write square root of 16. I know what the square root of 16 is. It is 4. Okay, here's what I said right there. 81 to the 1/2, I can write as 81, and I'm going to take the square root of it again. Taking that denominator. Okay, it doesn't have to be a 2, it can be other numbers. 27, and I'm taking the cubed root now. The cubed root of 27 is 3 because 3 cubed is 27. Uh-oh, what about this? Well, we need to recall that if we have a negative exponent, we need to move. Negative exponent means move. Okay, and you say move where? Move to the bottom. So I have 1 over 32 to the 1/5 power. Okay, when I moved it to the bottom, my 1/5 became positive, okay? Now I'm going to apply my rule that says how I can write this. I can write this as, 32. I'm taking the 5th root. I'm still just applying the rule that I just learned. And I know that the 5th root of 32 is 2 because 2 to the 5th equals 32. So here's my answer. Okay. So that has to deal with fractional exponents. Okay, well, there's something in common about all of these, and that is that you have a 1 as your numerator on all of them. So what if we don't? What if the fraction has a numerator higher than 1? Okay, well, the only thing that's going to change is the fact that you're going to say the nth root of a. That's what we just did. Then you're just going to raise it to the numerator. Okay. So now we have 16 to the 3/2. Just a second ago, we had 16 to the 1/2, but now we have to the 3/2. So we have the square root. Let's deal with your radical first. So square root of 16. We're dealing with our radical first. So we have, we're not going to put an equal sign because that might be a little wrong. Let's just put an arrow. The square root of 16 gives us 4. And then we need to raise it to the numerator that we're given. So we're going to raise it to 3 because we were given 3 on top. So we need to put it, we need to raise 4 to the 3rd power. That gives us 64. Okay. Let's do this one. It's a habit for me to put equals. All right, so we have 32 to the 3/5 power. And we're going to say, okay, we need to write this as, we're dealing with our radical first. So we have 32. And we're taking the 5th root of it because we did this. And we get 2 because 2 to the 5th is 32. And then we need to worry about our numerator. So we say, we're going to cube it. 2 cubed is 8. Okay. Now, let's work with rational exponents with variables. Okay, so those were all numbers, right? We didn't have any x's or anything going on in that. We just had numbers. What happens when we have variables? So I give you something like this, and I say simplify the expressions. All right, well, you're multiplying 2 things. And 3 times 7 hasn't changed to the fact that that's 21. When you multiply like exponents, so meaning when you have something like x and x, and you're multiplying those together, you add your exponents, okay? Multiplying variables with exponents. Multiplying, I'll say like variables. So variables that are alike with exponents means add exponent. Okay, so we're going to have x to the, and we need to add 1/2 plus 2/5. So we have 1/2 plus 2/5. I'm going to write this a little smaller. Okay, so we need a common denominator, right? Because we can't add these 2 fractions without having a common denominator. All right, so our common denominator would be 10. So we need to multiply this by 5 to get 10, and we need to do it to the top and to the bottom. We need to multiply this by 2 to get 10, and we're going to do it to both of them. So we get 21x to the 5/10 plus 4/10. Now we can add them, and we get 21x to the 9/10. 21x to the 9/10 would be our answer. So we're adding our exponents there. So we need to find a common denominator. Okay, so now we can divide them too, right? If we can multiply them, surely we can divide them. Once again, your whole numbers here, nothing changes from the fact that 20/5 is 4. Okay, so that dealt with those. Do you remember what we do with our exponents whenever we're dividing? We subtract, right? We stated that just a second ago. So we have 4 and 3/2. So we're doing 4 minus 3/2, right? So we need a common denominator again. We don't have it, and we have to have that when we add and subtract fractions. So we need a common denominator between 4 over 1 and 3/2. Okay, so that's obviously going to be 2 because we're dealing with 2 and 1. So we're going to say that our numerator needs to be multiplied by 2. So we get 4x to the 8 over 2 over x to the 3/2. So now we're saying 8 over 2 minus 3/2. Let's subtract those numerators and get 5/2. So we get 4x to the 5/2. Okay. I'll highlight my answer. So just taking that concept of multiplying and dividing these to the next step with throwing in some rational exponents instead of whole number exponents. All right, so we just have these two problems left for P3. All right, so here we have our fractional exponent here, but we know that we can turn this directly into a radical, right? So this can become the square root of 64x to the 11th y to the 18th. And you say, okay, well, how do you know it was the square root? Because we know that this denominator of our exponent becomes the root that we take, okay? Well, our number is easy, right? The square root of 64 gives us 8, no problem, okay? Then we have to think, all right, I have x to the 11th, y to the 18th, and I need to get these outside the house, like we like to say, okay? How we do that is we take our exponent and divide it by our root that we're taking, okay? So we're gonna do, for x, we're gonna do 11 divided by 2, right? Okay, well, 2 goes into 11 5 whole times. So that gives us 10, and we have 1 left over. Okay, so here's the important part. Whatever is left over has to stay under the house, okay? So we have 1 left over. So that means that x to the first, okay, one of our x's is going to have to stay in our house, but it went in 5 whole number of times, right? So that can come out. So we have x to the 5th, okay? Again, I'll say that one more time. I divided 11 by 2. And I said, all right, 2 goes into 11 5 whole number of times. That comes out of the house. And I had 1 left over that had to stay inside. Okay, so let's do y. That's going to be 18 divided by 2. That goes in 9 times. So that goes in evenly. So that means that all of our y's can come out and we're left with y to the 9th power. Okay. And I'll do some highlights here so that you can see where I'm getting our numbers from in our answer. Okay. There's where we get our 1 from and our 9 from. Okay. You don't have to write x to the first under the radical, so you can rewrite that as this, square root of just x. Okay. Now let's finish up with this one. Okay, so this time we again look at it and say, all right, I know something about fractional exponents that I can put it into a root. Okay, so I know I'm taking some root of 8x to the 14th power, y to the 22nd power. Okay, and because my denominator of my exponent is 3, I know that I'm going to have a 3 right here. So this time I'm taking the cubed root. Okay, so I'm taking the cubed root of 8. Okay, well, that's 2. Okay. Now I need to get x and y outside the house. So I need to divide, just like I did on the previous problem. So for x, I'm going to do 14 divided by, divided by 3. If I can draw a division sign. There it goes, divided by 3. Okay, so how many times does 3 go into 14? A whole number of times, 4. And we have 12, and we have 2 left over, okay? So this time, x to the 4th comes out, and we have the cubed root. Don't forget to write your cubed there. And we have x to the 2nd, okay? Because that's what was left over. That didn't go in evenly, so it had to stay under the house, okay? And now we need to do y. So we're going to do, let me switch colors. I cannot draw that. There we go. We have 22 divided by. And so it goes in 7 times with 1 left over. So we have y to the 7th, because that's how many times it went in evenly. And then we have 1 left over. So that means that one of our y's has to stay under. Okay, so if we wrote this all over again, all in the same color, without any highlights, it would look like this. Okay. So the main thing here is that you have to remember that you can turn these fractional exponents here into a radical. And then you just take the root of your number, right? That's the easy part. And then you have to remember that in order to get these exponents, variables and exponents outside, you need to divide your exponent by whatever root you're taking, right? That's what we did over here. And then the whole number of times it goes in to your exponent, you take it out. Okay, so it went in 4 times. I took x to the 4th out. However many are left has to stay under your house. Okay, so I had 2 left here. So I had 2, I had 1 left here. So I had y under my house as well. Okay, and that is P3.